Okay, let's see. First ever going over homework questions. Let's see. So we're doing, I gotta back this up. Still getting used to all of this. So we're doing assignment 11.2, matching slope fields. Already put the answers in work online, so maybe that's why there's not as many questions coming in through the Google form, which I'm going to use for each of these assignments. I'm going to go ahead and do a couple of these first ones, even though there weren't a lot of questions, just to kind of get us warmed up. And then there was a lot of questions on the last problem, so we'll get to that, I think, pretty quickly. These first problems, you're supposed to draw the slope field, or you're supposed to match the slope fields, which we talked about. And then on part B, it said then solve the differential equation for 1 through 3. And that should make sense. The answer you get should look like the shape that you saw on the picture. So you should have already matched these up without doing this work. So number 2, we have to separate the variables. You guys should hopefully be getting the hang of that. dy, y is on one side, left side, x's, dx is on the other side. There is no x. The antiderivative of this is natural log of y equals. Now, we're going to do it for initial condition. So we're actually going to get a c value. And I think that makes it easier. So let me zoom in here. So we're doing initial condition. So the antiderivative, just dx, that's a 1. So that's x plus c. Let's find the initial condition now. We're going to plug in y equals 2, x equals 0. And so we get c equals natural log of 2. We're going to rewrite it back with that value in there. X plus natural log of 2. Now we got to get y by itself. So we're going to exponentiate both sides. That's going to give you absolute value of y. Over here, we're going to use rules of exponents to break this up into multiplication, rules of exponents. That's going to give you a 2. So we have 2e to the x. To get rid of the absolute values, we've got to do plus or minus. Now, we should pick if it's plus or minus based off the initial condition. If I plug 0 in for x, I should get positive 2 for y, which would mean we got to go with the positive. Now, one of the other things that I've been talking about, that I talk about a little more in the next lesson, but we've been talking about, is that we need to also provide the domain. Now, this domain's all reals, so that's fine. That's not enough. You got to look at the original differential equation and say, is the derivative ever undefined anywhere for any values of y, which would impact values of x? Nope, we're all good. So the domain is all reals. We could write interval notation like that. So that is what we're doing on the second part of these. Now, the graph that you already matched up to 2 should look like an exponential. And that one looks like D. So, and if you to go even further and put in that initial condition and kind of follow that slope field, this is what you get. Now it's an exponential. That looks like that. We know how to graph exponentials pretty well. And so that makes sense. Now the negative ones down here were if you get initial condition, that leads you to selecting the negative, and the c value, instead of becoming a vertical shift like it does on a lot of functions, by the time we solve for y, it actually becomes a scaling factor, and it either affects the size of the graph vertically or if it gets reflected downward. So that's why we get that one. So that was number 2. Number 3, we're going to separate the variables, and I'm going to leave the negative on the right hand side. Don't lose it. And I always try and leave as much stuff on the right hand side as possible because we're going to have to get the y by itself eventually anyways. Now this is going to be y squared over 2. This is just power rule. Don't forget the plus c. Let's find the c now. We're using the same initial condition. So we plug in 2 in for y and 0 in for x. and that's 0, and c equals 4 over 2 is 2. And so then we get y squared over 2 equals negative x squared over 2 plus 2. And now we got to solve for y. So we're going to multiply everything by 2. That'd be what I would do first. And we get negative x squared plus 4. We're going to take the square root of both sides, plus or minus. It could be the negative. Don't not do that. Hopefully by now I'm picky. I'll probably take off points in your work if you don't show me that, because I'll just assume you got lucky if it's positive. Now this time when you plug 0 in, it should give you positive 2. So we're going to go with the positive. So this is our solution to the differential equation, but we also need to make sure we include the domain. The domain would be anything that affects the domain of this, which we know cannot be negative. It has to be greater than or equal to 0. And but we also know that we're not going to actually have to find the actual domain of this. We just got to find the one piece that our initial condition lies on. So that kind of lets us off the hook. Actually, kind of makes it work easier. So I'm not even going to worry about the inequality. I'll figure that out easily enough with the initial condition. So I do that, square root of both sides, plus or minus. There are two values, so plus or minus 2. The other thing you got to worry about is the original differential equation. Are there any values of x or y that cause that to be undefined? And in that case, y cannot be 0. Now, don't put that on I'm going to make a little number line down here. And I'm going to put negative 2 and positive 2. And I'm always going to put these as open dots for these kind of problems because it says our domain's a single open interval, including the initial condition. Always open, even though equals 2 is fine here. But actually right here, we'll find out. I mean, y equals 0. Don't put that down here. But there's an x value that causes y to be 0. And you would figure that out by using the answer you just found and setting equal to 0 and solving for x. Well, guess what? We just did that. So you're going to get x equals plus or minus 2, and that's not possible. Now, generally that's okay if a function has a derivative that's undefined. The function can exist there, it can be part of its domain, but because we're starting with this derivative, we can't use any values that it doesn't exist to find this answer. So it's always an open dot, and it has to include 0. So 0, I like to do this, like, all right, that's the piece that we want. So that's our domain. We could say domain, or we could say 4, negative 2 to 2. But you need to do that. Now we're looking for, what's this graph look like? Well, earlier on, it might be easier to recognize maybe at first. If we move this over here, it'd be x squared plus y squared with the same coefficients equal to, those are circles. So this is the top half of a circle. So if you go to the one graph that looks like it has circles on it, and if you were to do 0, 2, you could kind of follow the slope field. But whenever the slope is undefined, which is going to be vertical tangents right here on the edge of a circle, and it's just going to be the top half because of our initial condition. So that also kind of shows you, visually why we're not going to include those, because the derivative is not defined. Anyways, that should make sense with the answer you picked earlier. Number 5, sketch the solution curve through 0, 2. Well, that's right here, and we sketch it. And I really do want you to put arrows. Really want you to put arrows on the ends. So that's 0, 2, right? This is the specific solution or particular solution. Now, they already showed us 0, 1, which is already on the picture. They gave us the differential equation. They're asking us to solve it right now. And this is a possible question on the AP test. They might give you a slope field that's already done and ask you to sketch particular solution curves. 0, negative 1 would be down here, and it would look like this. And, I don't know. I think it's better to put arrows on the ends because it indicates that the solution keeps going past our picture, which is true. The XY plane extends forever. Part C, you have to solve the differential equation. So we just did that a couple times. You got to separate the variables. The y ends up in the bottom on the left-hand side. If you divide it, the dx ends up. You don't want your dy or dx to be in the denominator after you separate the variables. And we integrate. natural log of absolute value of y equals x squared over 2 plus c. That's power rule. Now we have an initial condition, 0, 2. So let's go ahead and find the c value right now. I just think that's going to be the easiest rather than dragging that c around. 2 in for the y, 0 in for the x. And that goes away. So our c value is natural log of 2. So then we're going to plug it back in, natural log of y, absolute value of y equals x squared over 2 plus natural log of 2. We're going to exponentiate both sides. I've done this a couple times. Rules of exponents do allow us to break up that exponent into separate bases that are multiplying each other. That's going to give you a 2. So we want to do that. Now to get rid of the absolute values, we have to do plus or minus. There's a 2 in front. E to the x squared over 2 is all in that exponent. Let's decide if it's plus or minus. If we leave plus or minus, that's 2 solutions, and we're trying to do a particular solution. So if you plug 0 in for x, you get e to the 0 is 1 times 2 is 2 is positive 2. We want the positive. And then, like I've been saying, we got to make sure we always write the domain with these. The domain of this on its own is all reals. You can plug any value of x in there and it gives you an answer. 0, negatives, positives. The original differential equation right here, any values of x or y cause that to be undefined, division by 0, even root of a negative, natural log of a negative or 0. Nope. So we're good. All reals. But you guys know I'm going to give you interesting ones coming up probably at some point. So that's number 5, A, B, and C. Number 6 is similar. Now, this is a differential equation on number 6 that we wouldn't be able to solve because we can't separate the variables on that. And I think I showed you in class the general solution for it, but you're not going to have to worry about that. But here's a slope field for it. And we could create slope field for that. We've done it. And we could sketch a solution on that slope field. So 0, 1 is like right here. Make sure you don't mix up your x's and y's. I've seen people do it a lot. And you see all these slopes that go right into each other. That is an asymptote, a slanted one. So you should realize that's happening and make sure you don't cross it. So that is part A. Part B is negative 3, 0, 1, 2. Negative 3 zeros over here. Negative 3 in the x, 0 in the y. And something like that. So we get kind of very different types of shapes on either side of this. And you could actually, if you started on that asymptote, you get a straight line. So that's number 6. And on the back, I'll go and do number 10 and 14. These are quick. Now, these might have tricked some of you guys. We're trying to match slope fields to these equations, not differential equations anymore. So these are super easy, and I'll admit you're not going to get anything this easy on the AP test, but it's still kind of interesting. Just change your mind. Some of you guys probably treat the differential equations like the way you are doing these ones and should. This one, these are the actual answers that these slope fields should represent. So we're looking for a slope field that has that shape. So we're looking for one that looks like it's a cubic. Well, the only one that looks like a cubic to me is like this one, right? So I think we're going to go with F for number 10. I mean, do you see any other one that could even be a cubic? Number 14, it's a natural log graph. Now, natural log graphs look like this. You guys should be quick with this. Natural log graph looks like that, right? But it has absolute values around the x on the inside. You guys remember what that does? That means that any negative you plug in is going to be forced to be positive, and you're going to get the same image on the left as in the right. So absolute values inside around the x of any function is going to reflect the right half of that graph onto the left half. And whatever was on the left half will go away. In this case, there was nothing. So you're looking for graphs that will look like that. And I think that one's G, right? G kind of has that look to it. Okay, number 5. This is where we had the most questions. Now you got to do a slope field, which most people didn't have questions on, but I like this one. Brings up an interesting thing. They tell you how many points to graph the slope field, which is this is like an AP question. It's actually from 2006. I don't know, it's old, but I guess slope fields haven't changed a whole lot in 14 years. Anyways, if you look at this graph, there's a lot of weird dots, and it's not like a nice grid like maybe you're used to. But look at them: 1, 2, 3, 4, 5, 6, 7, 8. Don't do any here, which I could see someone easily doing that. But the reason they're doing this isn't to be tricky. They're actually doing this to help you because those slopes are probably undefined. And I know I've been graphing some vertical slopes on some of these slope fields, but I've told you, I think usually that technically you shouldn't. Because how can you draw something that is undefined, which means it doesn't exist? So you can't, you're not supposed to. Sometimes it's undefined because it creates like a corner or something. So sometimes we're not even sure why it's undefined. But let's try some of these. I like to go for the zero slopes first. And that means that the numerator has to be 0. And that means that y equals -1 is where all the zero slopes are. And that's a horizontal line. So here and here, but don't put one there. The other reason I like to always emphasize that how many points they want is so that way I don't accidentally give extra points that I shouldn't have for whatever reason. And that I also give enough points. I don't miss any. Undefined would be when the denominator equals 0, which right there, that's the y-axis, and those are all the ones they're telling you not to put slopes on. So we're not going to. There might be some kind of symmetry across that, though. So we might just start plugging in some points. 1 for x, 0 for y would give you a slope of 1. -1 for x, 0 for y would give you a slope of -1. So you're kind of seeing that symmetry. 2 for x and 0 for y would be 1/2, so it's up 1 over 2. And -2 in for x will give you -1 over 2. And then 1, 1 would give you a slope of 2. And this would give you a slope of -2. So make sure that the slopes are getting steeper when they should be. Positive and negative, but 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay, good. I got them all. I didn't give any extras. Okay. And if they leave them out, they're not trying to trick you. They're actually trying to help you not graph slopes where you shouldn't. Okay. Part B, find the particular solution of the differential equation. They give you an initial condition, state its domain. They don't even need to tell you that. You need to state the domain automatically for this. But it's nice that they reminded us. So we need to separate the variables. Now it should only involve multiplication and division. So we got to move this whole thing over here. You can't like subtract the y. So we're going to multiply both sides by 1 over 1 plus y. I usually do this in my head, but you can write it. We're going to get rid of the dx by multiplying by dx. And so we have 1 over 1 plus y dy equals 1 over x dx. So that's separating the variables. That's worth 1 point out of 9 on free response problems. We're going to integrate natural log the absolute value of 1 plus y all together. Now, you could think of this as u substitution. That is an inner function, but it's a very simple one that you don't really need to go through all this. Like you get 1 over u du, and then you get natural log the absolute value u, and then you replug that back in, and that was not that bad. Natural log of the absolute value of x here, plus c. Don't forget the plus c. Now I'm going to find the c value right now. They give us this x and y value, so let's plug those in. +1 for the y, -1 for the x, plus c. Now natural log of +1 is 0. So c equals natural log of 2. So I'm going to rewrite that. And those absolute values are all still there. Now we're going to exponentiate both sides. We can't distribute that, but we can use rules of exponents to break up the exponents into the same base, multiplying. That's going to give you a 2. That's going to give you absolute value of x. So we have the absolute value of 1 plus y equals 2 absolute value of x. Okay, now we're just trying to get y by itself now. There's a lot of kind of algebra. To get rid of the absolute values, we do plus or minus. I'm getting rid of the ones on the left side, not the right side. I'm leaving those there. Now we should, I think, decide right now if it's positive or negative. If you plug in -1 for x, which gets forced to be a positive 1, you get 2, and you plug in positive 1 on the other side for y, you would get 2. So we want the positive. Now I'm going to go up here, so we're going to get y equals, now I'm going to subtract the 1 to the other side. So we have 2 absolute value of x minus 1. And that would be our solution. And we could say, well, but I'm going to tell you right now, any answer you get when you solve the absolute differential equation and it has absolute values in it, I guarantee you're going to be able to write the answer, the final answer, without them because of the domain. So we got to talk about what's the domain. The domain in this, all reals. And that's where some people be mistaken and just say that's the answer. You have to go back to the original derivative, which we had right here, and say, are there any values that cause that to be undefined, the derivative? And in that case, x cannot be 0. So if I were to do a number line and just put an open dot at 0, anything that causes an issue in the domain of this or the original derivative, I'm just going to put open dot, never solve it for these kind of problems. And then the initial condition was over here at x equals -1, right? So that's single open interval. The domain of this is all reals, but the domain of this as a solution to this differential equation is just this right here, from -infinity to 0. Now that -1 there, I'm just writing that to show me which piece to use, but it shouldn't break up my answers. Now, once I figured this out, then I realized that if I'm going to say this is a domain of this, isn't x always going to be negative for sure? And if I know what's inside an absolute value is always going to be negative, then I can write it without that for adding an extra negative. So our best answer is right here. And going back up to the slope field, we can kind of make a little more sense of this. If we were to sketch the particular solution here, -1, 1 is right here. Now, you're not asked to do this this time, but let's do it. If you were to do this, you would follow this line, and it has a slope of -2, so it should come all the way down here. And then you would maybe think that it goes all the way back up here. And that's a V graph, which looks like this absolute value equation. That's something you learned back in Algebra 1. But here's the problem. It's undefined here, not because it has a vertical or infinite slope. It's undefined here because there's a corner. And so what we've been told is that our solution should stop at any place it's indifferentiable. So we put an open dot here, and we would only include this side as our graph of our solution. You would not include this side. And then that's what the domain down here is saying. And by the way, this is just a line now. And the equation of that line is y equals -2x minus 1. So that's your best answer. And this is the answer I would want. Anyways, I hope that helped. And, good luck. And let's keep getting work done. All right.